So now ready to have an appropriately physicsy discussion of phase transitions, so going from one state of matter to another. And one way of talking about it is with the energy. So imagine that I have a block of ice, and I'm just going to put energy into the ice until stuff happens, and I'm going to keep track of two things. The amount of energy that I put in, we now know how to do that. I could take the known amount of energy and measure it through the specific heat of, like a copper plate, and I could put the copper plate in contact with the ice. The energy will flow out of the copper plate in the form of heat really quickly, and I could just do that accounting, and then I'm going to measure the temperature of the ice with a calibrated thermometer. So I measure the energy I put in, I observe the temperature that I get out. And what I'm going to see is, let's say we start pretty dang cold, like surface of Mars cold, is that I'm going to put energy in and I'm going to see the ice heat up. And the ice is going to heat up until I get to 0 degrees Celsius. So we'll put Celsius on that scale. And if you think about the units, essentially the slope of this more or less is the specific heat. So if we just had, like, for instance, 1 kilogram of ice, just to make the units work out, for 1 kilogram of ice, the slope of this really would be sea ice, because it would have joules per Kelvin, or inverse joules per Kelvin, I guess. So it would be 1 over the specific heat. But not important. The important part is the overall shape. So what happens when we get to 0 degrees Celsius? So 0 degrees Celsius is when something funny first starts happening. So we put energy in, more and more energy, but then the ice itself doesn't heat up. What happens is it turns into water, right? So there's 0 degree ice, and then after some amount of energy later, we get 0 degree water. And you can visualize this in some sense as, this model of a solid and a liquid and a gas are not amazing, but they're good enough in some respects. So you could think about a solid as a collection of atoms that are attached by springs. Right? So this is a solid, and it's characterized by strong bonds. And a liquid is categorized by, actually, it's not that there aren't bonds, they're just kind of flimsy, and maybe to really draw water, H2O. What that has to do with is the fact that water is a polar molecule, and the positive and negative clusters tend to attract each other. So this might look something like that, and that might look like that. And the water knows that the positives want to be near the negatives, for instance. So this is a liquid, and in general, a liquid is weakly interacting. And the reason I know that water is a weakly interacting liquid is because I can see it, the capillary action of a liquid crawling up the sides of a vessel. So going from this toy model to this toy model, really what happened was I had to put in energy to rip apart all of these bonds, these strong bonds, to turn it into a liquid. So that's where this energy is going. But the molecules themselves just don't have any more kinetic energy. I'm putting all that energy into bond ripping. And kinetic energy is temperature, so average kinetic energy. So I put that in. This is what's called the latent heat of fusion, and we'll get to that in a second. I've ripped them all apart, and now water, I increase the water in temperature until I get to 100 degrees Celsius. And then we basically do this again. So 1 over this would be 1 over the specific heat of water. And then I have to pull the same stunt. I've got to put in energy. I don't increase the temperature. And what this is doing is turning liquid into steam. So now I have gas. And gas is, if anything, repulsive. So but one way or another, these are very weak interactions. So this energy where I put a lot in and I didn't see any manifestation in a change in temperature, it's the exact same story as we had with the solid to liquid transition. All we did is we put the energy into ripping apart the bonds themselves. Okay, and then here is where things get really dicey. So you would say like, aha, now I'm just going to increase the temperature of the gas. Well, it turns out that, again, there are two ways of doing that. We could do this at constant volume or constant pressure. Um, and this whole, anything in between, honestly, you could have a collection of both. You could increase the pressure with like a sticky piston, where both P and V increase. But one way or another, this is steam. And gases, all bets are off. I can do a variety of things. So we kind of understand these because they're manifested by 1, in the case of solid and liquid, or 2, in the case of gas, specific heats. What we haven't talked about are those. And those have the names, the latent heat of fusion and vaporization. And this is what they represent. They represent not increasing kinetic energy. They represent bond ripping, essentially. So the solid to liquid and back transition, that's characterized by the latent heat of fusion. And, you know, if you're a sciencey person, you've consumed the Kool-Aid and you think about the words melt and freeze as very generic. They describe any change of phase in between solid and liquid. So melt means for anything at all, you know, like you can melt copper, certainly. Just a reminder that I'm not specifically talking about ice. So that's the so-called latent heat of fusion. And let's say that we actually measured this for an example, and I'll put on units. So this is denoted LF. It's SI units. So we're not changing the temperature. So unlike specific heat, there's no divided by degrees Kelvin or Celsius. So really all this is joules per kilogram in SI. What you'll honestly see a lot of places is kilojoules per kilogram or joules per gram, to be honest. But those are the SI ones. So you could do this experiment. If you had a kilogram of water, you would discover that the latent heat of fusion for water, specifically for the ice water transformation, and you'll see why we don't really use SI units for this. It takes an astonishing amount of joules per kilogram to melt ice. So in fact, in the middle of the 19th century, people would saw blocks of ice out of ponds in New England and literally sail them down to India, and they would, you know, because it takes so much energy to melt ice, they would show up intact and you could sell them as a delicacy. So let's do this. 333 kilojoules per kilogram, or 333 joules per gram. So again, that's why you see those. Okay, and similarly, we can define the latent heat of vaporization. So that would be this one, going from the liquid to gas barrier. So that's LF, the energy put in to seemingly do nothing, at least as far as temperature is concerned. And LV, when we from liquid to gas, we say we vaporize it. The other way it's condensed, but this is called latent heat of vaporization. Okay, and there we go. Latent heat of vaporization is the energy per mass required to change from liquid to gaseous phase. And for water, it's a little bit less. It's really the vaporization. Ice is magic, to be perfectly honest. Um, so LV is about 2,200 or something. Yeah. LV is 2260 kilojoules per kilogram. Okay. So sorry, more than the latent heat of fusion. And water, again, is miraculous. Okay, so we can add this to our kind of roster of calorimetry problems. And what we do is I would keep this as like a roadmap in your mind. So far, the calorimetry we've been doing is confined within one phase. But now what we can do is we can put in so much energy we have to change the phase of matter. Or in fact, you might not have all the energy you need and be left with something that's half ice, half, well, there would be half ice, half water, and everything's at 0 degrees Celsius. So keep that picture in the back of your mind. Let's just jump right in and do melt some ice. And we'll do it in such a way to remind you of something that you'll probably see more than a few times from mechanics. We'll talk about power, not just energy. So rounding up quite a bit, especially in Seattle, this is the intensity of sunlight. This is watts per meter squared. So watts, again, are joules per second. So what this would be is 500 joules per second per meter squared, which means if I have a 1 meter by 1 meter block of sidewalk, every second 500 joules of sunlight falls on that, which is like quite a lot, but it is quite a lot. And let's say that we're going to melt some ice on a lake or something like that. So I've got some ice cube, maybe, you can think about this as like 4 by 5 centimeters is the part that's being irradiated by the sun. So 20 centimeters squared. And we'll do this as easy as possible. We'll make it 0 degree ice, so it's already kind of up there. So we have 0 degree ice and 50 grams. And we want to know how long, so that would be time before it melts. So we'll add the time part, the joules part, last, and really just showcase the whole latent heat of, in this case, fusion. So I have, essentially what I have is 50 grams of ice at 0 degrees Celsius, and I want to know how much energy it takes to melt. And then this tells me how much energy I'm putting in as a function of distance and time, or space and time. Okay, so latent heat of fusion, I'll use joules per gram. I got grams. So I have LF times M. This is the heat energy required to melt the thing. And as long as I match units, I should be okay. So Q is in joules. This is 333 joules per gram, 50 grams. We're in good shape. So straight up, this would tell me joules. So that takes 16.65 kilojoules, or 16,000. Okay. And now the question is, how much does that deliver? So we have an intensity, which is 500 watts per meter squared. And the reason to do this is this encapsulates all the other ways that you'll see energy per time and energy per area. So you may as well get them all out of the way. So the way that you deal with something like intensity is just you unravel the units as need be. Okay, so the first thing I'm going to realize, and this would get me what's called power. So power is watts, energy per time. Power would be intensity times surface area. And I got to make sure my units match. So there are two ways of doing that. I could say that this is 500 watts per meter squared. And then I would multiply that by 20. I got to turn centimeters into meters twice, so that's times 10 to the minus 4 meters squared. And then that would give me just plain old watts. Okay. So I'll do this in the dumbest way possible. So that's 10,000 times 10 to the minus 4th watts. And then we could move that over 4. So that's 1 watt. Oh my goodness. Is that right? Isn't that so nice? Yeah, it's 1 watt. Okay. And this would be 1 joule per second. Okay. I need 16.65 kilojoules. I get 1 joule every second, so therefore I have to wait 1,600 or 16,650 seconds. Right? So doing that in more detail, so 16,650 joules times, equals my 1 joule per second times the time I need to wait. So we'll call that delta little t because we use big T a lot. So this is a time, joules per second times seconds gives me joules. That obviously is 16,650. And that turns out to be like 4.6 hours. Sure, 4.6 hours. Okay, so what's the moral of the story? Because a 50-gram ice cube at 0 degrees Celsius isn't crazy, and that really is the sunlight. So, your ice cube probably melts in less than 4.6 hours. So odds are the culprit in your melting ice cube is the fact that the drink is warm, more likely. And we'll talk about other ways of getting energy into and out of stuff. Okay, so in the problem-solving session, we'll talk a bit about efficiency, but I just want to show off some calorimetry problems with at least one of these latent heats and give you guys a kind of big chunky one with all of them at some point in the not too distant future. Okay, so let me just point out one thing. About the names of the latent heats. And this is probably something that you would expect based on the fact that, energy is conserved. If I want to go from solid to liquid, I have to use the latent heat of fusion. And if I want to go from liquid from gas, I use the latent heat of vaporization. If I want to go from gas to liquid, I actually use the exact same quantities. It's just their names are kind of asymmetric. Fusion talks about going from liquid to solid in some sense, and vaporization talks about going from liquid to gas. So they're kind of like liquocentric, if that's a real word. But just realize if you're going the other way, use the same LF. Okay, so let me do one more ice problem, and then I think we're basically done with ice. And this is more of a pure calorimetry problem, not with funny units. Let's just put a kilogram of ice or water into the freezer and figure out how much energy it takes out of it to freeze it. So my suggestion is to use this kind of roadmap where we have the latent heats. So first and it doesn't have to be precise, but basically we have ice that we can heat up and cool down. We've got to rip the ice bonds apart to make liquid, and then we can heat up the liquid, and then we can vaporize the liquid to make gas, and then we can do all sorts of funny stuff with gas. Again, you can go forward or backward. So I just want to kind of sketch out what's going on my particular trip. So I have 1 kilogram of water at 20 degrees Celsius, so that would be in the water phase. And then I've got to freeze it, and then I've got to cool it down a little bit. So if I do this right, I've got to cool down the water, freeze it, and then cool down the ice by 2 degrees as well. So I should actually have 3 parts of my calorimetry problem if I do this right. And as such, I would need to know 3 things, 2 specific heats and 1 heat of fusion in this case. So step 1, let's cool down some water to the point where we can freeze it. And how I do that is call this Q1, so the heat required for step 1. So that's C, that's water. That's M, and that's delta T, right? So just plain specific heat. And I know the specific heat of water. Let's use SI, because why not? Always do that, 4186 joules per kilogram degrees Celsius. And we have 1 kilogram of water, so at least something's going for us. And then so the statement of the question is, how much energy does that take? So I'm assuming that the question is, more than assuming, the question essentially is like, what's the power bill? What does the power company got to say about this? So I'm just going to make everything positive. So the delta T is we go from 20 to 0, so that's 20, and positive is good in this case. Right? And so therefore Q1, I would get 83,720 joules. Okay. Now, next thing I have to do, step 2, is I've got to freeze the water. And to be like hyper pedantic about it, technically what I'm doing is I'm freezing 1 kilogram of 0 degree water into 0 degree ice. So that's Q2, and that's latent heat of fusion. We're actually really fusing it in this case, M. And so that's 333 kilojoules per kilogram times 1 kilogram. So that's 333 kilojoules. We wrote that as joules, so I'll write this as joules. Just to, again, point out some of these like kind of astonishingly big numbers for water. And the hippies are right about one thing. Water is actually like fairly miraculous. Okay, and then step 3 is this last step. We've made some ice. Now we've got to cool the ice to its final -2 degrees Celsius. After we fuse it, it starts at 0 degrees Celsius. And then the statement of the problem says that we end at -2 degrees Celsius. Okay, so what's the thing that I have to look up that I haven't written down, I don't think yet? That would be, can't use this. I would have to find, and it's different, so every phase of matter has its own properties. I would have to look up the specific heat of ice. Can't use water. Still 1 kilogram though. And again, we're talking about the energy we put in, so that's all positive too. And the specific heat of ice is 2,100 joules per kilogram degrees Celsius. We got 1 kilogram of the stuff. And again, the change in temperature is 2 degrees because, again, what we're asking about is, basically the energy that we would have to put in. So all signs just kind of made to be positive. And then Q3, in that case, 2,100 times 2, so 4,200 joules. So that was pretty easy. Okay, so finally we just add them all up. So the total amount or if you just want to be like really pretentious, you can say the sum of all Qs. I don't know. 420,920 joules. Okay. Here's a kilogram of water. Basically, you're filling all your ice cube trays. This, if I were to maybe take like 100 kilograms of person, so chop off 2 zeros and then realize that that's, another 10 for G. It's about enough energy to climb Mount Everest. Maybe like a third of the way or something like that. So maybe the best way of saying it is for the 1 kilogram block, it's enough energy to take the 1 kilogram of water up Mount Everest 5 times. So again, there's a lot of energy in thermal motion that you can extract or you can put in. And again, the point of all of the mechanical and technical progress of the 18th and 19th centuries was kind of realizing that that's true and we can tap into it. Okay. One last thing, because why not? I will leave this kind of as a puzzle. This idea is kind of wrong in a bit of a sense. So let's say that I have a glass of drinking water. I mean, wrong isn't right, it's just incomplete. And I slosh it and I spill it. Okay? So I got some drops of water. What happens when I come back in half an hour? They're gone, right? My conclusion from that, of course, is that clearly the ambient temperature in this room is 100 degrees Celsius because they vaporized. So that can't possibly be right. So this, again, does not tell the whole story of things like vaporization. There's a lot of other stuff going on. So if you want to know like what's going on with the atmosphere of Mars or the moon, there's a lot of other things like cosmic ray ablation. The thing that's going on with evaporating of drops is actually has something to do with distributions. So if you look at the Boltzmann distribution and you ask about the number of particles at each specific speed, and you get this funky thing that goes up quadratic, down like a dying exponential. And at this tail, there are things, a small number of them, but there are things that are going pretty dang fast. This is where evaporation happens. So not this. This is what we're talking about when we talk about temperature. So temperature, the best thing that temperature describes are the behavior of particles around this mean. These guys have a ton of energy. It's really easy for them to just like fly out of the water droplet, and then eventually they get depleted. The rest of this kind of thermalizes again, gets depleted, and so on and so forth. So evaporation kind of happens at the tail end of this behavior that's not really well categorized by this. I'm just pointing it out if you are, at some point you're confused and realize that I'm telling you all sorts of like simplified fairy tales about thermodynamics. It's true, I am. But this one you can definitely unravel because we have talked a bit about distributions, is evaporation happens out here. But this stuff that we're talking about with latent heat of fusion is best characterized by that.